Hello, my name is Helen, and welcome to my video for Lab 2 for Physics 2212. Alright, so in this lab we are going to be expanding upon the experiment that we performed in Lab 1, and we are going to be doing the same thing. We're creating and observing interactions between two charged pieces of tape. Our goals, however, are to expand upon the computational model that we created and create a model that more accurately analyzes the behavior between those two charged pieces of tape. And then the overview of the main result for this experiment was the charge found by the modified computational model was 2.6 times 10 to the negative 8 coulombs, which is about 2 times the original value that we found in Lab 1. And then for a bit of context, here are some fundamental principles that we're going to be using. Similar to Lab 1, we're still going to be using the equations for electric force and electric field. But in addition to both of those, we're also going to be using the superposition principle, which says that if we find a charge on an infinitesimally small piece on a given body, we can then integrate over the entire object to determine the total charge. All right, and then to give a bit of an overview of our experiment from Lab 1, we had two 17 centimeter pieces of clear tape. We had the system and surroundings. Initially, both tapes were a distance from each other with identical charge, neither tape close enough to exert a force upon the other. We are assuming that there's no drag and that each piece of tape has the same charge. And then the charge on the tapes was determined to be roughly 1.25 times 10 to the negative 8 coulombs. And so for the process, we created two charged pieces of tape. We observed their initial interactions, and then we made one piece of tape float by suspending it and bringing another charged tape into close proximity. The distance and mass are recorded, and we made further calculations to determine the number of excess electrons and excess charge on the tape. So our calculations for that were as follows. We were able to use the electric force equation and balance it with gravity to determine that the charge was roughly at this value that we got earlier. And so for Lab 2, we use the same material system, surroundings, and conditions, and the experimental process also remains the same, but the experiment gets different when we go into our computational model. Rather than originally modeling both pieces of tape as point charges, we're now going to create a model that simulates both of the pieces of tape as objects rather than points. And we're going to use the superposition principle that we talked about earlier to find the sum of the infinitesimal charges on the tape. So here we have the mass of the tape. This is in kilograms. And then we have a function right here that creates the objects in the model, which you can see right here and right here. And so we're taking n number of really small pieces of tape, and then for each piece of tape down here, we are able to find the electric force on that specific part. And then this white arrow is the sum of all of these smaller green arrows. And so because the system is isolated, we can say that the top and the bottom forces have to balance out. And so we're able to plug in different values of charge for our piece of tape to make this relationship true. And that is the value that we get right here, which is about 2.6 times 10 to the negative 8. So to compare the models from the experiment, our original model was just so stupid, but it modeled both of the pieces of tape as a point charge. It also took into consideration the effect of gravity. And then our new model, we can see here, is able to more accurately show two pieces of tape where they are, two true objects. And then it also shows the amount of force that is exerted by the bottom tape on the top tape. And so the new charge was determined to be 2.6 times 10 to the negative 8 coulombs, which is about 2 times larger than the original value that we found in experiment 1. And so this experiment utilized the superposition principle, which requires the expansion of an infinitesimally small piece onto a full object. Here we calculated this as the sum of 15 small pieces along the tape, but the larger that this number gets, the more accurate that becomes. So for what if we had modeled each of our tapes as a single point charge? So the process and results of experiment 1 can actually point us towards what this indicates for the model. So as we did in that experiment, the forces in the tapes are able to balance quite neatly, which allows for a lot easier calculations and quicker arrival to an answer. But because of this oversimplification, it's likely the value returned is not truly accurate, which actually brings us into our next question, which is why do these estimates differ? So the computational model created in this experiment is able to more accurately represent the two pieces of tape for what they actually are, as opposed to simplifying the calculations by treating them both as point charges. Because our model is more accurate, the value that we return is much more likely to be closer than the actual value. All right, thank you guys so much for watching. Have a great day.